I am Satya, Assistant Professor, Department of Computer Science from KCS Kasinada College of Arts and Science, Chennai 21. In this video, we are going to see about critical section problem in operating system. What do you mean by critical section? A section of code common to n cooperating processes in which the processes may be accessing the common variables. A critical section environment contains entry section, critical section, exit section, remainder section. In entry section, code requesting entry into the critical section. Critical section, code in which only one process can execute at any one time. Exit section, the end of the critical section, releasing or allowing others in. Remainder section, rest of the code after the critical execution. The critical section must enforce all three of the following rules. The first one is the mutual exclusion. In mutual exclusion, no more than one process can execute in critical section at one time. Progress, if one is in the critical section and someone wants to enter into the critical section, then those processes not in the remainder section must be able to decide in a finite time who should go to in the critical section. Bounded waiting. All the requesting processes must eventually be let into a critical section. There are so many problems, software problem, hardware problem, as well as the semaphore. And Peterson's solution is one of the solution given for the critical section problem. It is a two-process solution. There are two instructions, load and store instructions. They are atomic, that is, that cannot be interrupted. The two processes share two variables. In turn, Boolean flag of two. The variable turn indicates whose turn is to enter into the critical section. The flag array is used to indicate if a process is ready to enter the critical section, then the flag of I should be true, implies that the process PA is ready to enter into the critical section. This is the solution to the critical section problem. We are assuming that the code preceding the critical section and which control access to the critical section is termed as the entry section. It acts like a carefully controlled locking door. The code following the critical section is named the exit section. It generally releases the lock on someone else's doors, or at least lets the world to know that they are no longer in their critical section. The rest of the code are not included in either the critical section or the entry or exit section is termed as the remainder section. Here, we are having the turn. In this, the turn is marked as I. So, only the process PI can enter into the critical section. And after the completion of the PI process, the turn is turned into J. That implies that now process PA can enter into the critical section. Then the remainder section are actually has the code to be executed. Peterson's solution is a classic software-based solution to the critical section problem. It is unfortunately not guaranteed to work on modern hardware, but it illustrates a number of important concepts. Here, two processes P0 and PA, which alternate between the critical section and remainder section. That is, PA implies this process and the other process is the PJ. If the turn is indicates as I, then the process I is allowed to enter the critical section. At the same time, the flag variable is also set. It sets that which process wants to enter into their critical section. In this example, the I is the current process, J is the other process. In this example, the same code running on two processes at the same time. Here, in the algorithm one, we are explained by using the turn. We are saying the turn for I and the process J is to wait. After the completion of the process I, the turn is J, turn into J, and the process J is now can enter. And here the flag is set. The flag is used for the process. Each process maintain a flag, indicate that it wants to get the critical section. If it check the flag of the other process and does not enter the critical section if that other process want to get in. First, the flag is set as false for to the process. If any one of the process set the flag as true, then that process is ready to enter into the critical section, and the next process has to wait until it becomes false. This is the Peterson solution, and in this solution, each process sets a flag to recurse entry. Then each process toggles a bit to allow the other is first. This code is executed for process I, and process J, the same code can be repeated. Here, the two variables, Boolean flag off as well as the turn, is also used in this algorithm. Initially, the flag is set as false. Then the flag of I is set to true to indicate that the PA is ready to enter into the critical section. Whenever the two variables are set as true, that is, in the intersection process I is first raises the flag, indicating a desire to enter into the critical section. Then turn is also set to J to allow the other process to enter the critical section if process J so desired. The while loop is busy loop. Notice that the semicolon is at the end, which makes process I wait as long as process J has the turn and wants to enter into the critical section. Process I lowers the flag of I in the exit section, allow process J to continue if it has been waiting. Next, hardware solution. In the hardware requires to support the critical section must be have. First, the indivisible instruction. Second, atomic load store test instruction. For instance, if a store and test occur simultaneously, the test gets either the old or the new, but not some combination. The two atomic instructions, if executed simultaneously, behave as if executed sequentially. In synchronization hardware, many systems provide hardware support for critical section code. Uniprocessor and multiprocessor. Uniprocessor could disable interrupts. Currently running code would execute without preemption, generally too inefficient or multiprocessor system. Operate system using this not broadly scalable. Modern machines provide special atomic hardware instruction. Atomic means non-interruptible, either test memory, word, or set value, or swap contents of two memory words. In process synchronization, does the sequence below work on a cached multiprocessor? Initially, location contains A0 and location B contains B0. Processor 1 writes data A1 to location A. Processor 1 set B to B1, indicating data at A is valid. Processor 2 waits for B to take on value B1 and loops until that changes occur. Processor 2 reads the value from A. What value is seen by processor 2 when it reads A? That is A equal to A0, B equal to B0. Here, the write ordering, the first write by processor will be visible before the second write is visible. This requires a write-through catch. Sequentially consistency, if processor 1 writes to location A before processor 2 writes to location B, then A is visible to all processor before B is. To do this, not catching shared data. The software solution discussed should be avoided since they require write ordering or sequential consistency. The hardware test set on a multiprocessor causes an explicit flush of the write to main memory and update all the processor caches. Imagine to write all shared data straight through the cache. With the test and set, only locked locations are written out explicitly. In not too many years, hardware will no longer support software solution because of the performance impact of doing so. Thank you.